So, okay. So yeah, I'm going to talk about all this stuff, and let me just review what we did in the last two lectures. So these lectures are about graph sparsification. In the first lecture, we proved that every weighted undirected graph has a weighted subgraph H with n log n over epsilon squared edges. So these Laplacian quadratic forms are 1 plus epsilon closed. And this was achieved by a random sampling algorithm where you sampled each edge with probability proportional to its effective resistance. And the way we derived the algorithm was really by converting this into a linear algebra problem where we turned each graph into a bunch of vectors which were decomposing the identity, and then we sampled them according to their squared norms, which turned out to be the effective resistance. But then, this was not, this is sort of pretty, it was not clear that this was optimal because of this log factor. So in the second lecture, I showed you how to improve this bound to 4n over epsilon squared. So you get rid of the log n. And this is by a deterministic greedy algorithm that's based on adding one edge at a time, which corresponds to rank 1 updates of these matrices. And the way we did this is that we, figured out a way to see what these rank 1 updates do to the eigenvalues in terms of some sort of repelling electrical charge model. And then we had this barrier function that we used to, analyze how these eigenvalues behave and guide the choice of the next edge. And, well, there was some deterministic algorithm that got this bound. So the thing is that this is still not really the end of the story because this bound is 4n over epsilon squared, and the graphs that we produce are weighted undirected graphs. So in particular, if I apply this to the complete graph on n vertices, I get a weighted graph with 4n over epsilon squared edges, which is this kind of approximation. But I actually know that for the complete graph, the correct answer is 2n over epsilon squared, and I don't actually need these variable weights. Right? So remember this example that I showed you in the beginning, like the first example of sparsification. If you take the complete graph and you take d random matchings, where d is 2 over epsilon squared, then with high probability, when you reweight the edges by n over d, this thing is a 1 plus epsilon approximation. Since the complete graph has eigenvalues all equal to n, this is just saying that the eigenvalues of this random graph lie between n times 1 minus epsilon and n times 1 plus epsilon. And since all the weights are the same, they're all n over d. You should really think this is an unweighted graph. So in particular, if I scale the weights back to 1, then I just scale the eigenvalues down by a factor of d over n. And the statement at the bottom of this is really that if you take d random unweighted matchings, then the eigenvalues are between d times 1 plus minus epsilon. And actually, if you actually care about the second order terms, the precise statement is this. This was proven by Friedman. It's a very difficult thing to prove, that if you take d random matchings, the eigenvalues are between d minus 2 square root d minus 1 and d plus 2 square root d minus 1, plus some little of 1 factor. All right? So this was this is the precise statement for what happens when you take d random matchings. And this is better than what we were able to produce because it's a regular graph. We didn't guarantee anything like that in the things that we constructed, and it's unweighted, and it has this better bound. So now the question is, can you get this kind of exact bound without weights? Okay, so that's what I'm going to talk about today: how to get a regular unweighted sparsifier of the complete graph with these bounds. And why am I beating this complete graph to death? Like, why do I care so much about sparsifiers of the complete graph? Well, unweighted approximations of the complete graph are also called expander graphs, which you've heard Luca talk a lot about. And they're sparse, well-connected graphs, which are these two properties that it's kind of difficult to get them at the same time, and they behave like random graphs. All the edges all the cuts have lots of edges leaving, random walks mix quickly, etc. And they're sort of a very useful general pseudo-random object in computer science that it's used all over the place. So now in this talk, I'm going to talk about adjacency matrices. So far I've been talking about Laplacians. But it's going to turn out to be more convenient to talk about adjacency matrices for this particular case of the problem. And this is not a big deal because if you have a d-regular graph, then the Laplacian is just d times the identity minus the adjacency matrix, right? So, I'm going to talk about adjacency matrices that have real eigenvalues, and the eigenvalues are just d minus the eigenvalues of the Laplacian. And let me just review some really basic facts about these adjacency matrix eigenvalues, which you also heard from Luca. So if the graph is d-regular, then the top eigenvalue is equal to d. That's easy to check. If you plug in the all ones vector here, because the row sums are equal to d, you just get that the all ones vector is an eigenvector with eigenvalue d. And it's also not difficult to see that if the graph is bipartite, then the eigenvalues are symmetric about 0. So if lambda is an eigenvalue, minus lambda is also an eigenvalue. And these two facts are completely general and they hold for all graphs. So I'm going to call these trivial eigenvalues because they're, well, they don't tell you anything about the graph. Okay, so with this, in terms of the adjacency matrix, definition of expander is the following. It's a good expander if all the non-trivial eigenvalues are small. So you have these two eigenvalues at d and possibly minus d. I want everything else to be close to 0. So instead of talking about approximating the complete graph, I'm going to talk about all the eigenvalues being close to 0, which is the same thing. And for example, here are some really good expanders according to this definition. If you take the complete graph on d vertices or the complete bipartite graph, then all their non-trivial eigenvalues are actually equal to 0. So they're the best. But really what we want to do is construct an infinite family of such graphs. We don't just want to do it for some fixed finite n. We want to be able to do this for some n going to infinity, keeping d fixed. And it's not possible to construct an infinite sequence of graphs for which all the non-trivial eigenvalues are equal to 0. In fact, there's a limit to how well you can do this. This was shown by Laurent Bapana in 1986, that for any infinite sequence of graphs, you cannot make the eigenvalues concentrate in any interval that's smaller than this, minus 2 squared d minus 1 to 2 squared d minus 1. Okay? You cannot get better eigenvalue concentration than this interval. And you might be wondering what this number is, and this number has a meaning. It comes from a particular object, the infinite d-array tree. So this is an infinite graph, which is, well, it's a tree where the branching factor is equal to d. It's an infinite graph. It turns out if you write down its adjacency matrix and compute its spectrum, which you can do, it's literally equal to this interval, minus 2 squared d minus 1 to 2 squared d minus 1. And so the content of Laurent-Bapana's theorem is that this graph is the best possible deregular expander from a spectral point of view. So the theorem just says that the best graph is this infinite graph, and this is how good it is. So the goal is to get the same bound for finite graphs, okay? And that gives us the definition of a Ramanujan graph. So a Ramanujan graph is called Ramanujan if all of its non-trivial eigenvalues have absolute value at most 2 squared d minus 1. So it's as good a spectral expander as the infinite deregular tree. And I already told you that if you take a random deregular graph, union of d matchings, it's pretty close. So it has eigenvalues 2 squared d minus 1 plus little o of 1. So it's not actually a Ramanujan graph according to this definition, because it doesn't actually match the behavior of this tree. But it gets pretty close. But then importantly, there's this amazing independent results of Margulis and Lubatsky-Philip-Sarnak, who showed that when d is equal to p plus 1 or p is a prime, there are infinite sequences of Ramanujan graphs which are deregular. And these graphs were Cayley graphs. The proof of this uses some deep number theoretic results. But there's a really explicit construction and has proved to be useful in computer science. So this is very nice, and it leaves open this sort of funny question that what if d is not equal to prime plus 1? Okay, so it turns out you can do it for d equal to a prime power plus 1. That's due to Morgenstern. But it was actually not known whether these things exist for d not equal to prime plus 1. And sort of the conceptual point here is, do these things exist because of number theory, or do they exist for some generic reason? So what I'm going to tell you about today is a resolution of this question in the bipartite case. So the main theorem is this theorem with Marcus and Spielman. It says that when d is greater than or equal to 3, there's an infinite family of bipartite Ramanujan graphs. Okay. So bipartite means it has trivial eigenvalues of d and minus d. And the theorem states that for every d, there's an infinite sequence where the other eigenvalues are 2 squared d minus 1.
What happens if I know people do experiments, if you take a random deregular graph and check if it's...
Big mystery. We don't know. There are various bets going on about this. What is the probability? No, it's a fantastic question.
It definitely cannot be probability. It's definitely bounded away from 1.
That's not proved, I think.
No, proof. No, I'm not asking anything about proofs. Only about what's observed, just to know.
Why do they keep finding Ramanujan graphs with
Can you
reasonable
tell us
probability?
what the discussion is about?
Oh, so the discussion is if you take a random graph, what's the probability that it's Ramanujan?
And what on irregular graph, the large random, what is the probability that it's Ramanujan? Many people have thought about this, it's completely optimized.
Isn't there some conjecture that it's 52% or something? Is that your conjecture?
It's not my,
No, no,
definitely not.
Okay. There's a
There is
conjecture
an-
that's
I think
Tracy
there is an
Whittle.
ongoing bet between Peter Samak and Noga about this.
Okay. I see. About
Noga thought
the
it's
number.
almost certain, I think Samak thought it's almost certainly not. And
Oh, so it's not either,
that is
right?
still open.
I see.
You
Okay.
said there's a conjecture about the distribution?
There's a conjecture that the distribution is Tracy Whittle, which is the same as the distribution of the largest eigenvalue of a Gaussian matrix, which would give you a number. Okay, so that's the theorem. And the proof is not based on number theory. It's completely elementary, and I'll show you the proof today. And there's one major caveat here, which is that this is an existence proof. It does not give you a way to explicitly construct these objects. So it's not useful for algorithms or anything like that. And it's based on something called the interlacing families of polynomials. And if you went to the last talk, this is this whole dream sequence with the expected polynomials. It's an actual way to prove something using expected characteristic polynomials. Okay. So the way we do this is we prove, we follow an approach given by Bilu and Nikhil. So what do we want to do? We want to construct an infinite sequence of deregular graphs with a spectrum that's concentrated. So to do that, it would suffice to find some operation which doubles the size of a graph without blowing up its eigenvalues too much. So what I would like to happen is sort of in this picture, suppose I have a graph, suppose it's Ramanujan, so its eigenvalues are in this interval. I want to find some operation which gives me a graph on twice as many nodes, and maybe this adds some new eigenvalues or moves the eigenvalues a lot, so it doubles the number of eigenvalues. But I want to find an operation so that these new eigenvalues also lie in the interval. And if I can do this, then certainly I can just keep iterating this and get an infinite sequence. So Bilu and Nikhil gave a very nice operation, which they conjectured has this property. So it's called a two-lift, which is the same thing as a two-cover. So let me define what a two-lift is. So suppose I have a graph on n vertices, which I'm going to call the base graph. So the two-lift is a graph on two n vertices. And it's obtained as follows. So first you make two copies of the original graph. You get the two n vertices. So now you have two disconnected copies of the original graph. And now what you do is, so there are two copies, and each vertex has A0 and A1. So each node now has two copies. And now what you do is you look at each edge, and if I look at this edge C0, if I look at the edge CD, now there are two copies C0 D0 and C1 D1. So you look at each edge, and right now the edges are parallel. You look at each edge, and you either leave it parallel or you cross the two edges. So you make this binary decision for each edge. You either leave it as C0 D0 C1 D1, or you cross it and make it C0 D1 D0 C1. All right. So if there are m edges in the base graph, you have to make m decisions. So for every edge, you have to decide to leave it parallel or not. So there are m decisions. There are 2 to the m possibilities. There are 2 to the m possible lifts of a given graph. And this thing that you get at the end is called a lift. It's a graph on 2 n nodes, and it's also deregular. Okay. So the really nice thing about two lifts is that the eigenvalues of this two lift are related in a very nice way to the eigenvalues of the original graph. So the first thing to note is that the eigenvalues of the two, all of the eigenvalues of the original graph are also eigenvalues of the two lift. So this is an easy exercise that you can prove. That you can, it's a sort of linear algebra fact. But what's really nice about two lifts is that the new eigenvalues of the two lift can actually be described very concretely as follows. So given a two lift, you associate the lift with a signing of the adjacency matrix. All right? So you take the adjacency matrix of the original graph, and for each edge that you crossed, you turn the 1 into a -1. So for the original graph, it's just a 0-1 matrix. In a two-lift, you have this binary decision for each edge, and whenever you crossed, you turn it into a -1. Keep maintaining symmetry. So this is called a signing of the adjacency matrix. And as you can see, it's the same thing as a lift. There's a bijection between signings and lifts. And now there's this very nice theorem of Bill and Nikhil, which shows that the eigenvalues of the 2-lift are literally the union of the old eigenvalues and the eigenvalues of this signed adjacency matrix. So if you want to reason about the spectrum of the 2-lift, all you have to do is look at this adjacency matrix that contains all the information, the signed adjacency matrix. And they made this really bold conjecture in their paper, which is that every d-regular graph has a 2-lift in which all the new eigenvalues have absolute value at most 2 squared t minus 1. All right. So this is actually a conjecture about all graphs. So any graph, it doesn't have to be Ramanujan. There exists a 2-lift for which the new eigenvalues meet this bound. And well, because 2-lifts are the same thing as adjacency matrices, what this means is that every d-regular adjacency matrix A, that's just a 0-1 matrix with zeros and 1s, that's just a 0-1 matrix with row sums equal to d. That every d-regular adjacency matrix has a signing, so the norm of the signing is at most 2 squared t minus 1. That's a pure linear algebraic conjecture of matrices. And they proved that this is true, not with 2 squared d minus 1, but with this bound of square root d polylog d, which is also quite a good bound. It's very close to square root d. And by iterating this, they constructed expanders with eigenvalues contained in this interval. So what we did is we proved this conjecture for bipartite graphs. That if you have a bipartite graph, there's a signing of the adjacency matrix for which the norm of the signing is at most 2 squared d minus 1. And this bipartiteness comes in a very simple way. So recall that I said that, okay, so it comes in as follows. So the theorem we actually prove is this. Every d-regular adjacency matrix has a signing, so it's the largest eigenvalue of the signing is at most 2 squared d minus 1. So this is the maximum eigenvalue. It's not the maximum absolute value of the eigenvalue. So we only control the top eigenvalue. We don't control the bottom eigenvalue. But then recall, what I said earlier. The eigenvalues of bipartite graphs are symmetric about 0. So if it's bipartite, if you control the top eigenvalue, you automatically get the bottom one for free. So our weaker theorem for bipartite graphs implies that the norm is bounded. Implies that the absolute values are bounded. That's the only way bipartiteness comes into this argument. And you can check that taking a lift preserves bipartiteness. So this is enough to do the construction for bipartite graphs. Okay, so let me tell you how to prove this theorem. So the task is pretty simple. You're given an adjacency matrix. You need to find a signing with small norm. So one natural idea is to choose the signing randomly. So just for every edge, with probability half make it plus 1, probability half make it minus 1. And unfortunately, if you do this, then it appears that the expected norm of the signing, the expected norm is strictly bigger than 2 squared d minus 1. So in expectation, certainly this thing is not Ramanujan. It's not awful. So Bill and Nikhil showed that if the base graph is nearly Ramanujan, then its expectation is order square root d polylog d. So it's not way off. But it's definitely not going to get you this bound. So random signing is not going to work. It's not something. It's okay. I'm not going to say it's rare, but it's something you have to look for at least a little bit. Okay. So what do we do instead? So the main novelty in this approach is to study the roots of this of this signed adjacency matrix, or study the roots of any matrix by looking at it through the characteristic polynomial. So what I'm interested in is the largest eigenvalue of A sub s, which is my signed adjacency matrix. So observe that this is the largest root of chi of A sub s, which I'm going to use to denote the characteristic polynomial of A sub s, which is just determinant of xi minus A sub s. All right. So this is just it's a linear algebra fact. The eigenvalues are the same as the roots of the characteristic polynomial. And the main idea is to look at this object, the expected characteristic polynomial of a random signing of the adjacency matrix. So you give me a matrix, I look at all possible signings. For each one I get a polynomial. I literally average these polynomials. And this is literally what it looks like. It's a coefficient-wise average of the polynomials. So this a priori is a little bit weird because what I wrote up here, what I'm really interested in is the roots of these polynomials, right? And this averaging, I'm averaging the coefficients of the polynomials. and the relationship between roots and coefficients is, nonlinear, certainly. So, I mean, something, in general, very mysterious things can happen when you just average polynomials. So the punchline is that the polynomials here have some very special structure, which we call interlacing family, which implies the following fact, that there exists, if I take the expected characteristic polynomial over a random signing, there exists a specific signing, a single signing S. So the largest eigenvalue of the characteristic polynomial of that signing is at most the largest root of the expected characteristic polynomial. All right. So I'm able to compare this funny object that I got by averaging coefficients. I'm able to compare its roots to the roots of the individual polynomials. Okay. So this is the main device in the proof, and given that this is how I'm going to proceed, there's a sort of clear 3-step plan to proving this theorem. So the first is to prove what I just claimed, that there exists some polynomial in this collection which does as well as the expected characteristic polynomial. And I just want to reiterate that this is very different from the usual kind of averaging argument where you would say that there exists a polynomial whose largest root is at most the expected largest root. So that's a trivial statement, right? The key is that here I've taken the expectation inside the largest root operator. So this is very different from just the usual averaging argument. Okay, so once I can do that, I now need to figure out what the expected polynomial is. So in the second step, I'm going to calculate the expected polynomial. And the expected polynomial turns out to be an object which is very well studied in algebraic graph theory called matching polynomial. And the third step is to show that the expected polynomial's largest root is what I want it to be, right? So this also, it turns out to be exactly what I want, 2 squared d minus 1, and this is also due to some classical, it's due to some work in statistical physics, which I'll tell you about. But once I can do these things, I'm done, right? Together, these three things imply there exists a signing whose largest root is 2 squared d minus 1, which proves Bigelow and Mendel's conjecture. So let me start with actually parts 2 and 3, because they've already been done, it turns out, and they'll tell you that it's worth trying to do part 1. So let's calculate the expected polynomial. So a priori, this could be anything, right? Even though the individual polynomials have real roots, I'm adding exponentially many of these polynomials. This polynomial may not even have real roots, right? It could be anything. So it turns out Gottesel and Gutman have already looked at this 30 years ago. And what they showed is that for any graph G, if you look at the expected characteristic polynomial of a random signing of if it's adjacency matrix, you get the matching polynomial of the graph. So let me tell you what the matching polynomial is. It's a univariate polynomial. It's of degree n if the graph has n nodes. And it's a generating function which counts the number of matchings of various sizes in the graph. So the matching polynomial of a graph G on n nodes, the coefficient of x to the n minus 2i is the number of matchings with I edges. All right? So here's an example of what this looks like. Here's a graph, and here's its matching polynomial. It's a 6-vertex graph. It's a degree 6 polynomial. And, there's one matching with 0 edges. There are 7 matchings with 1 edge, because there are 7 edges in the graph. There are 11 matchings with 2 edges. And there are 2 perfect matchings. So that's it. I just compute these numbers, and I get this polynomial. And this... so you can see, for example, the constant term of this polynomial just counts the number of perfect matchings, which is something you might have thought about. So that's the matching polynomial. And the theorem is that the expected characteristic polynomial of a random signing of an adjacency matrix is equal to this. And here's the proof, or here's a very simple proof. So the proof is just to expand this expression using permutations, right? It's an expectation of a determinant of xi minus a sub s, where xi minus a sub s is a random matrix that looks like this. So it has x's on the diagonal, and it has random plus minus 1 variables on the off diagonal, and on the rest of the entries, which correspond to edges. And you have, for every edge, you actually have 2 entries, which are going to get the same value. But apart from that, they're IID. So all the signs are plus minus 1 IID. Okay, so here's the proof, right? So you expand the determinant using permutations, right? Determinant is the sum of products over permutations of the entries. So let's look at the contribution from different permutations. So suppose here's a permutation. Suppose I have a permutation that includes any 0 entries. Well, I get 0 because it's a product. And if I have a permutation that only takes 1 entry for any one of the edges, I also get 0 because it's an expectation of this entry. It's an expectation of this product, and these entries are independent. And the expectation of each of these entries is 0. So if I just get 1 term coming from any edge, I get 0. So the only terms that survive consist of terms on the diagonal and both entries for particular edges. But these just correspond to swaps if you're thinking about permutations. So the only permutations that are non-zero are these involutions, and these are just matchings. These are literally just matchings in the graph. And well, you can calculate. You see that if you compute the expectation of a term like this, you get a square of this, which is 1. So it just counts the number of matchings. That's the proof. You just expand in permutation. Okay, so we know what the expected polynomial is. It's the matching polynomial. Okay, so is that a good thing? Turns out it's a really great thing. So this matching polynomial was defined and looked at 40 years ago by Hellman and Wiebe in 1972 in the context of statistical physics. And they proved, first of all, that the roots are real. So that's also not obvious, right? If I just write down some generating function, the roots can be anything. So they proved that the roots are real. And the roots are absolute value at most 2 squared root t minus 1. Right? So that's exactly the number that we need. Now the proof, at this point there are a bunch of ways to prove this. So they proved it using, basically by writing down a recurrence for this polynomial, like what happens with this polynomial when you delete a vertex or delete an edge. And by studying this recurrence, they could, well, quite elementarily in less than a page, but it takes some care, they could prove that the roots are at most 2 squared root. But there's also a very nice sort of more conceptual proof due to Godsill, which is in his book on algebraic graph theory, which gets the same bound and gets it from this infinite deregular tree. So roughly speaking, what Godsill's proof does is, so what Godsill shows is that this matching polynomial divides as a polynomial the characteristic polynomial of a certain tree obtained from the graph by looking at paths, basically. So a certain large tree obtained from the graph called the path tree. So Godsill proves that this thing divides the characteristic polynomial of the path tree. The path tree is a tree whose degree is bounded by D. So it's an induced subgraph of the infinite deregular tree. And that's a connection. So this number really comes from this infinite tree. So that's great. So the largest root of the expected polynomial, which is the matching polynomial, is exactly what we want. And so all we have to do is show the first part, that there exists some polynomial that does as well as this expected polynomial. Now, so this turns out to be implied by the statement that this collection of polynomials is an interlacing family. But basically, what do we need to do here? We need to understand what averaging polynomials does to the roots of the polynomial. Right? So we're interested in the roots, but we're averaging the coefficients. We need to understand how these things affect each other. So, the most vanilla question that we need to answer is the following. Suppose I have 2 polynomials, and suppose they have real roots. And suppose I compute their average, which is this expectation. So when are the roots of the individual polynomials nicely related in some way to the roots of the expected polynomial, the average polynomial? So in general, things can go quite wrong. So here's a canonical bad example. The polynomials are x minus 1 squared and x plus 1 squared. So they're quadratics. They have real roots, clearly. And clearly, when you add them, you get a sum of squares. So you get something that's just positive. It doesn't even have real roots. So adding real-rooted polynomials does not preserve real roots, let alone the locations of the roots. And this is not some degenerate situation with multiplicities. This is typically what happens. If I take 2 polynomials, like here are some polynomials with roots 1, 2, 3, 4, and I average them, I get something with weird looking roots. So typically when you average real-rooted polynomials, you'll get things that have, well, not even real roots. But there are some examples where something good happens. So here's a canonical example where something really nice happens. So suppose the polynomials are again quadratics, but they're moved so their roots alternate, as shown in this picture. So the roots are 1, 3, and 2, 4. So then if you calculate the average, which is this purple polynomial, you'll see that each root of the average polynomial lies in the convex hull of the corresponding roots of the individual polynomials. So the roots of the average end up being some kind of averages of the roots, not with the same distribution, but they end up lying in the convex hulls of the roots. So in particular, they're real, but we also know where they are. So this is great, and this is what we would like to exploit. So the main concept in this proof is that there's a sufficient condition that tells you when this happens. So if you have some polynomials that you want to average, and you want to say the roots of the average are in the convex hulls of the roots of the individual polynomials, there's a nice sufficient condition, and the condition is called common interlacing. So what's a common interlacing? So I already told you what interlacing is yesterday, but let me just write down the definition again. So polynomial of degree n minus 1 interlaces a polynomial of degree n if their roots alternate as shown in this picture. This definition also works for two polynomials of degree n in the obvious way. So that's the definition of interlacing. And I'm going to say that two polynomials or a family of polynomials have a common interlacing if there's a single third polynomial that interlaces all of them. Okay. So this allows you to prove this very simple and useful theorem, which is the following. If you have two polynomials P0 and P1, which are real-rooted and monic, I guess I should have written that, so they're monic and real-rooted. If you have two polynomials that have a common interlacing, then the largest root of one of them is at most the largest root of the average. All right? And the proof of this theorem is really simple. I'll just show it to you on the slide. So here's the proof. So here are my two polynomials, P0 and P1. They're cubics, they're monic, and they have real roots. So what I've assumed is that they have a common interlacing, which is a quadratic polynomial, which interlaces both of them. So the roots of the quadratic look something like this. There are these stars, alpha 1 and alpha 2. And the roots of the common interlacing split the real line into three intervals, right? Three intervals. And each interval contains exactly one root of each of my individual polynomials. That's what it means to have a common interlacing. Each of these intervals has exactly one red root and one blue root. So let me look at these intervals, and let me shrink these intervals so that their endpoints are now actually roots of these polynomials. So just shrink them so they're snug up against some of these roots. And I'm interested in the largest root, right? So let's look at the largest interval. So observe that to the right of this interval, both polynomials are strictly positive. That's just because the polynomial is monic, so it goes to infinity as x goes to infinity. However, I know that each polynomial has exactly one root inside this interval, so it changes sign exactly once inside this interval. So what that means is at the beginning of the interval, each polynomial has to be non-positive because it changed sign, right? So that means that in particular, any average of these two polynomials has to be positive to the right of the interval and negative at the beginning of the interval. So because it's a continuous function, it means it has to be 0 somewhere inside the interval, the expected polynomial. And then in particular, the root at the bottom of this interval, which is the root of the red polynomial, is at most the largest root of the expected polynomial. So I find a root of the expected polynomial inside this interval by this averaging argument, and that shows me it's at least the least largest root of the individual polynomial. So that's literally the proof. Okay, so this sounds very simple, but this is all we need to reason about these averages. Well, okay, it's not all we need, but this is sort of the main thing. Okay, so this observation by itself is yes.
So this condition that you have a common interlacing seems kind of strong, and I was wondering if you can weaken it to get the same conclusion.
Yeah, you can. So if you only care about the largest root, you actually just need one guy here. You need some interval where these guys change sign exactly once. You don't need all of them. This actually implies something much stronger, that the kth root of the average is contained in the convex hull of the kth roots of the individual polynomials. What it turns out that this weaker condition is fine, but there's no systematic way to prove it. Whereas there turns out to be a very nice systematic way to prove existence of common interlacings, which I'll get to in a moment.
And can't you control the last roots using the same thing by considering the last interval?
Yeah, so the problem with this averaging argument is that it only gives you one root at a time, right?
Yeah.
So, I mean, this doesn't prove that there's a single polynomial whose largest root is less, yeah. So if I want both those things, then, yeah.
It's
So this,
actually not true that you can.
Yeah, it's also
control all
false.
the-
Yeah.
you can-
it's also false.
Let you
Right, okay, that's true, yeah. The argument doesn't give it and it's false. There are easy examples where you have distributions where it's just false. Sure, okay.
If they're not interlacing, do you get a complex rate?
No. So there are examples where this is not just an only if condition for real rootedness. There are examples where you can add polynomials without a common interlacing and have real roots, and they're in the right place, but or they're not in the right place.
If you want any linear combination of your polynomials to have all real roots, then they must interlace each other.
Yeah, that's what I'm going to get to. So I'm going to get to that in a few slides. Exactly. Any convex combination. Okay. Okay, so that's the theorem about common interlacing. And this, so this is useful if you have a bunch of polynomials that have a common interlacing. We have exponentially many polynomials, one for every signing of the adjacency matrix, and they don't have a common interlacing. It's a very large collection of polynomials. So instead, we have this method for inductively applying the theorem on the previous slide, which we call interlacing family of polynomials. So this is just a device for systematically applying this this common interlacing observation inductively. So here's the definition. So I have a set of polynomials, p sub s, indexed by 0, 1 to the m. So for example, indexed by signings of a graph on m edges. So it's an interlacing family if you can place it on the leaves of a binary tree. So it's an interlacing family if they all have real roots and harmonic, first of all. All the individual polynomials are real roots and harmonic. You can put them on the roots of a tree. And then you can define the polynomials on the internal nodes to be the sum of the polynomials in the subtree. All right. So here are my original polynomials. And if I go one level up, I have p naught, which is the average of p naught naught and p naught 1. And p1 is the average of p1 naught, p1 1. So the internal nodes are just indexed by initial segments of these bit strings. Okay. And then the root is just the average. The root is just the sum of all the polynomials. So this is the definition of this tree. The nodes are indexed by polynomials. And you should just think of the internal nodes as, you should think of the root as being the expectation of all the polynomials, and the internal nodes as being conditional expectations, conditioned on some of the things being fixed. So if you have such a tree, and every pair of siblings has a common interlacing, then we call that an interlacing family. Okay, so every node that I look at, I want the two polynomials that are to sum of to have a common interlacing. Okay, and then this gives a very easy theorem by induction. If you have something that's an interlacing family, then there exists a particular leaf. There exists a particular polynomial in the family whose largest root is the most largest root of the root of the tree. So, and the proof of this is just induction, right? So you start at the root, and now I know that its two children, p0 and p1, have a common interlacing. So that means the largest root of one of them is at most the largest root of the root, right? And now again, I get some polynomial. Again, its two extensions have a common interlacing. One of them does at least as well as that polynomial. I just follow this out to the roots. But this is also, I mean, it's a trivial induction argument. It's also called a method of pessimistic estimators. So that's it. So if you have polynomials like this and all these common interlacings exist, you can set the bits one by one. So instead of trying to do it in one shot, you find this thing by setting bits one by one. And what we prove is that, getting back to our situation, if you look at the family of polynomials indexed by signings of a graph, signings of an adjacency matrix, that is an interlacing family. And that will prove the first part. Okay, so how do we prove this theorem? Well, looking at the definition, you need to prove that a whole bunch of common interlacings exist, right? So again, the internal nodes, I want to think of them as conditional expectations. So the leaves are indexed by signings, which are bit strings of length m. The internal nodes are indexed by partial signings, which are bit strings of length k. So S1 through Sk are the signs we've already set. And
So
then
the tree is precisely the tree of the signings.
Yeah. It's the same thing. I'm not sure why I'm saying it so many times. But, and then the polynomials at these internal nodes are just conditional expectations. And what you need to do is find a common interlacing for each one of these internal nodes. So you need to prove that all these exponentially many common interlacings exist. And this seems kind of daunting where you're going to pull these common interlacings out of, but well, it turns out there's this very nice characterization which, due to Fisk, let's say, but also has been known at least as far back as 1980 due to Fell, which says that existence of common interlacings is the same thing as certain real rootedness statements. So here's the dilemma. Suppose P and Q are monic and real rooted polynomials. There exists a common interlacing R of P if and only if all convex combinations have real roots. So this is exactly what you said earlier. And okay, this is like a 3-line proof, so it's a good exercise. You can try to find this. But it's really powerful because it turns this existential statement into a for all statement. Instead of trying to pull this out of somewhere, you now have to verify a bunch of real rootedness statements. So this sort of is also why these weaker conditions are, as you were asking. This makes it possible to prove that these things exist. Okay, so we're going to use this to prove that all of our common interlacings that we would like exist. And so what do you have to do? Well, for every internal node, you need to prove that every convex combination of its two extensions is real rooted. So there's some parameter lambda, which is this convex combination. I need to prove that given a partial signing S1 through Sk, if I look at the convex combination lambda times the extension with 1 plus 1 minus lambda times the extension with minus 1, then this is real rooted. And I'm now just going to observe that this is actually just a statement about an expected characteristic polynomial over all the polynomials, but with a biased distribution, right? So this is this sort of obvious fact that conditional expectations, I've conditioned on fixing S1 through Sk to be something. That's the same thing as just picking a distribution which is deterministic on X1 and Sk, and is random on the things that you've not fixed, right? So the polynomial I'm interested in, what does it do? So S1 and Sk, S1 through Sk are fixed. Sk plus 1 is plus 1 with probability lambda and minus 1 with probability 1 minus lambda. That comes from my convex combination. And the rest of them are just plus minus 1 with probability half. Okay? You seem to not, Christos.
Just my thoughts.
Yeah. So the content of this is you can just encode conditional expectations by looking at biased distributions because there's a product structure here. Okay. Because these signs are independent, that's important that the signs are independent. So in particular, all of the common interlacings that I wanted are implied by the following single statement, that the expected characteristic polynomial is real rooted for every product distribution on the entries of S. So remember the matching polynomial is the expected characteristic polynomial to the uniform distribution, which is a product distribution. But now suppose for each entry, for each edge, I assign a different bias. Could be lambda, could be deterministic. That gives me a different product distribution. I need to show that all of these guys have real roots. If I do this, then it implies that all the common interlacings exist. And this is literally the polynomial. It's the average of the characteristic polynomials with these biases lambda I, where these can now be anything. And you can view this as a generalization of Hellman and Lieb's theorem. So they showed that this has real roots when all the biases are half, or all the probabilities are half. We need to do it for arbitrary probability. Okay, so this is what we need to prove. And it turns out that to prove this, so to find the structure in these polynomials that causes this to happen, it's useful again to go back to Laplacians in some sense. So I shifted to adjacency matrices, but now I'm going to go back to Laplacians. So my expected polynomial is the expected characteristic polynomial is the expectation of P sub S under some product distribution on signings. Well, I want to show that has real roots, right? I want to show this has real roots. Real roots don't change if I shift everything by D. So it suffices to show that the expected polynomial in X minus D has real roots. And what is that? That's the expected determinant of Xi minus Di minus A sub S. So previously I just had A sub S here, and now I have a Di here. And if there's no signing here, you recognize this, it's just a Laplacian. So you should think of this as a signed Laplacian. And what is the point of doing this? Well, if I was just previously, if you just look at the adjacency matrix, you can write it as a sum of rank 2 matrices times the sign variables Sij. So because each edge appears in 2 entries, you have this matrix is just the entry that has a 1 in ij and a 1 in ji. You can write it as that matrix times a plus minus 1 random variable, right? But when you do this translation by D, you get this nice factorization into outer products, just like you do with the Laplacian. So remember that the Laplacian can be factorized in terms of these outer products, one for every edge. And it turns out that the signed Laplacian, which is just the signing of signed adjacency matrix shifted by di, this also has the same factorization. So it has terms that look like delta I minus delta j transpose. These are just my incidence vectors for all the signs that get a 1. And then it has terms that look like these incidence vectors but with a plus sign for all the signs that get minus 1. All right? So for a random signing, this is a sum of outer products, and which outer product you get for every edge is random. It depends on which sign is chosen. And now this is really sort of and it's important to observe that this is, well, it's a sum of rank 1 outer product, so it's positive semi-definite. So this is a very special kind of matrix. It's a sum of independent random rank 1 matrices. So this is the structure that we really need to get our hands on to prove that this thing has real roots. Once you do the shifting, you observe that this expected shifted characteristic polynomial of a random signing is the expected characteristic polynomial of a sum of independent random rank 1 matrices. So for every edge ij, you have a random vector vij, which is in red, and it's equal to, well, either the incidence vector or the incidence vector with the sign flipped, depending on whatever the bias is. So it's a product distribution for every edge of the bias. And now my polynomial of interest is literally the expected characteristic polynomial with some independent random rank 1 matrices. And now we prove that this is the master sort of theorem, we prove that all such polynomials have real roots. So this is a big generalization. So given any independent random vectors v1 through vn, which are in red, so the ones I'm interested in came from shifts of the signing, but now any random vectors, their expected characteristic polynomial has real roots. So this in particular implies what I want. And how would I prove this? So it seems sort of general that this average could contain a lot of terms. So to do this, we sort of follow this philosophy which has been around in statistical physics for a while, which is that if you want to prove that a univariate polynomial has real roots, often it's useful to look at it as a restriction of a multivariate polynomial. So it's often easier to prove that multivariate polynomials have real roots. I'll get to what that means in a moment. And use that to deduce results of a univariate polynomial. And the reason, roughly speaking, is that the space of transformations that preserve multivariate real rootedness, which I'll describe in a moment, is much richer and more flexible than what you get in the univariate case. So this is what we're going to do. So let me tell you what a multivariate real rooted polynomial is. So it's called a real stable polynomial. And this is the definition of real stability. So suppose I have a polynomial p in n variables x1 through xn. It's real stable if every univariate restriction in the strictly positive orthent is real rooted. Okay, ignore this last line. I mean, there's a notion for polynomials with complex coefficients, but ignore it. So it's a real polynomial with real coefficients, and it's real stable if all restrictions in these positive directions are real rooted. So the picture is like this. So here's a real stable polynomial. And here's a restriction in the positive orthant. And the point is that this should intersect in exactly the right number of places. So let's say it's a degree 4. This should have 4 roots for any line that you look at. Okay, so any restriction in the positive orthant, you should have all real roots. Not saying anything about.
The F and the P are opposite.
I'm sorry. There's no F. There's a P. Excuse me? Yeah. I'm sorry. There was some slide hacking here. There's a P. So.
The slide that we
Yeah.
don't see.
So the picture is just this. You take this is a bivariate polynomial. Its roots are some sort of curves in the plane, and then I mean, and then when you look at these restrictions in the positive orthant, the real restriction, these should all intersect in the right number of places. And we don't care about what happens in restrictions in other directions. So certainly a univariate polynomial that's real stable is real rooted because it has only one restriction, which is itself. Okay, so this turns out to be a really great notion. So let me first show you an example of a real stable polynomial, which is a very canonical, useful example that comes up a lot. It comes from determinants. So this is proved by Borchet and Brandon in 2008, but I think it's been folklore for longer than that. And what it says is if you have some PSD matrices A1 through AK, then the determinant of some Zi AI, where Zi are the variables, this is a real stable polynomial. Okay, the proof of this is 2 lines, and I've written one of the lines here. You literally just write down what a restriction of this polynomial means, and you observe that it's always the determinant of it's always equal to the characteristic polynomial of a symmetric matrix. Use this positivity condition to, I mean, you can do this exercise. I skipped the one line, but anyway, okay? So this comes down to the fact that characteristic polynomials of symmetric matrices have real roots. So this class of polynomial is always real stable. Now the really fabulous thing about real stability is that it has very well characterized and strong closure properties. So the set of operations which preserve real stability is really rich, well understood at this point, especially since the work of Borchet and Brandon, which gives almost sort of gives a characterization of operations preserving stability. But okay, we actually, I'm sorry, there's some more slide hacking. There's an alternate definition of real stability here. It's the same thing, but you can use this definition here. The univariate restrictions are real stable. This is an alternate equivalent definition. But anyway, real stability is preserved under many operations, and 2 of those operations are the following. One is setting any variable to be a real number. All right. This also has like a 3-line proof. If you know complex analysis, it's a nice exercise. And the other fact is that it's preserved under certain differential operators. So if I take a real stable polynomial and subtract off a partial derivative with respect to any of the variables, this is still real stable. So this is a multivariate generalization of the way I proved Cauchy's interlacing theorem, or maybe not exactly, but it's a generalization of the fact I told you yesterday that subtracting off the derivative preserves real roots and generates Laguerre polynomials. Here also subtracting off a partial derivative preserves real stability. The proof of this is also basically the Gauss-Lucas theorem. It's a theorem for like proof. So this was proved by Lieb and Sokal in 1981. So that's all we need. So I'm going to use these 3 facts to prove that the expected characteristic polynomial of any sum of independent random rank 1 matrices is real rooted. So the proof comes down to a formula. It comes down to an identity, which is this. Okay, so the whole proof is this identity. The identity says that suppose you have V1 through Vm independent random vectors, and their covariance matrices are AI, then the expected characteristic polynomial of the sum of Vi transpose is equal to this. So what is this? So there's some sort of multivariate characteristic polynomial. It's a determinant of xi plus some zi. So for every random vector I now, I have a variable zi. Some of zi ai, where ai are the covariance matrices. So these are expectations of V transpose. I look at this multivariate characteristic polynomial. Then for each I apply this differential operator, which subtracts off the partial derivative with respect to I. And I have m of these. Right? So I apply these m differential operators. This gives me some m plus 1 variate polynomial. Then I set all the extra variables to 0. That gives me a univariate polynomial. The identity says that this is equal to the expected characteristic polynomial of some of independent random rank 1 matrices. Okay. Now, this is, it tells us many things. So first of all, this is a sum over exponentially many polynomials. Here, in some sense, what I've done is I've taken the expectation inside. Right? The covariance matrix is the only place where the expectation appears here. And a priori, it wasn't even clear that this is a function of the covariance matrices. But this tells you that this polynomial is a function of the covariance matrices. Now, the proof of this, is based on a single principle, which is something I also told you about yesterday, which is if you take a matrix and add random rank 1 updates, add a random rank 1 matrix, it corresponds to subtracting off a derivative of the characteristic polynomial. So that's something I proved to you yesterday in the context of sparsification, but it turns out to be true here also. So this you can prove in half a page, and there's a very nice 3-line proof due to James Lee, which I encourage you to ask him about or find. But basically, it's easy to prove once you decide to. Yes.
So AI are not rank 1.
No, AI can be anything.
Anything,
AI can be
right?
anything.
Your rank 1 update key principle applies nevertheless, right?
Yeah, random rank 1 updates on the left-hand side. Yeah.
And that's-
So yeah, adding independent random rank 1 matrices generates these differential operators, which give you this representation for this polynomial. Rank 1 is very important. It's super false for rank 2.
I see, you take the expectation inside of the end.
At the end, yeah, after
Yeah,
you do.
after doing all this, yeah.
Well, I mean, in each step, you sort of take the expectation inside. The expectation turns into a differential operator, basically. One way to think of it is that these things let you write a generating function for the expectation. Okay, so once you have this, that's it. That's pretty much it, right? So here's the proof of the theorem. This is a determinant of some of PSD matrices, which is real stable, which I just told you. These differential operators preserve real stability. Setting things to 0 preserves real stability. So this whole thing is real stable, but it's univariate, so it's real rooted. Okay, so just the existence of this formula, that's the whole proof. But again, this rank 1 structure is what we're using. So once you have this, you're done, right? So I just showed you that any expected characteristic polynomial of some of independent random rank 1 matrices is real rooted. A specific case of this is the expected characteristic polynomial, the shifted expected characteristic polynomial of a random signing for any product distribution on the signings. And now you see why I did the shifting to get the rank 1 structure. This implies that the expected characteristic polynomial for any product distribution itself is real rooted, which implies that this is an interlacing family. So everything has common interlacings, which implies that there exists a signing which does as well as the expected polynomial, which completes the proof of the theorem. Okay. And which then proves this conjecture and shows that every graph has good lift, and you get an infinite sequence of Ramanujan. Okay, so some of the the point of this this argument had essentially two important components. So we used it to prove the existence of a certain matrix, right? And the interesting thing here is that we reduced this combinatorial problem of finding this matrix to analyzing some expected polynomial, proving that some polynomial has real roots, analyzing its roots. This is an analytic problem, it's not a combinatorial problem. And the first part where we proved real rootedness and interlacing, all these things, we did this using very generic facts, such as the matrices are rank 1 and this real stability theory. And the second part we did using matching polynomials and combinatorials. Okay, so I want to end by just saying one more thing. So we've now figured out exactly what happens for the complete bipartite graph. But what if I wanted to get unweighted sparsifiers of general graphs, right? So this is not possible in general. So this is the example that I showed you in the first talk that shows it's not possible. For the dumbbell graph, you need weights that are order n as 1. But what if I give you, and then the reason essentially is that this, now that you know about effective resistances, the reason is that the edge in the middle is very high resistance. But what if I gave you the hypercube, right? So all the edges are equally important in the hypercube. There's a lot of symmetry. There's no reason to expect that you need weights. And nonetheless, the theorems that I showed you still produce weights. So it turns out that you can prove the following theorem using techniques similar to what I just told you about. You can prove that if all the edges in a graph have resistance order n over n, which is the average resistance, then you can partition the graph into unweighted sparsifiers, each with n over epsilon squared edges. So what it's saying is, given the hypercube, which has n log n edges, you can partition it into log n graphs, which are literally just unweighted graphs, each of which is an approximation of the original graphs. And this is actually just a consequence of, I guess I'm out of time, so I'll just go over this quickly. This is a consequence of the following theorem, which says, if you have any graph with bounded resistance, if you have a graph with bounded resistances, you can partition it into two subgraphs, such that the quality of approximation is 1 plus alpha, where alpha is a bound on the resistances. And recursing on this produces this unweighted sparsification theorem. And this is a special case of some theorem about decompositions of the identity. Just as everything else I told you about sparsification was, this is a special case of this theorem, which says given any decomposition of the identity, if the norms of the vectors are bounded, then there's an unweighted partition into two sets, each of which approximates the whole. So remember previously I told you how to find a weighted sparse subset which approximates the original set. Here it's literally a partition, no weights. And the proof of this is based on expected characteristic polynomials. So it's based on interlacing families and the techniques that I just showed you. And this can also be used to prove a bunch of other stuff. So let me just quickly review what I told you about. So the first is I showed you how to get sparsifiers with n log n edges in nearly linear time using effective resistances and viewing this graph as a bunch of vectors. And then I showed you in the second talk how to get order n edges, but in n to the fourth time. So the algorithms are getting more and more useless. And this is based on this electrical charges model. And now I showed you this really useless thing, which is how to get sparsifiers with no weights when it's possible, with order n edges, but in 2 to the n time, by doing these random expected polynomials. And yeah, so I'm going to end with open questions. Okay, so there are some obvious ones I want to talk about today. Can you do non-bipartite graphs? So this all works for bipartite graphs. It's not an algorithm, and I said the running time is currently 2 to the n, because computing these polynomials is sharply hard. So can you get an approximation? I think this is a very interesting direction. And then from yesterday's talks, there's a few good questions left as well. Is there a fast algorithm for this order n size sparsifier? This would actually be very useful. So people who actually use this have emailed me on many occasions saying, they really want to get rid of that log n. Can you improve this to 2n over epsilon squared? I actually don't know, right? This is off by a factor of 2. And is there a fast combinatorial algorithm for the distances? So yeah, that's it.
Questions, comments?
So in some sense, right, like this use is sort of like the probabilistic method, and it's in that sense simpler. You're saying like there exists an value which is less than the expectation.
Yeah.
Is there any situation where you can get sort of a concentration bound in interlacing families?
So that's a really good question. So I think it's very interesting because in general you cannot. So in general there are examples where the good polynomials are exponentially rare. So I think a very interesting question is to characterize when this happens with high probability. And I think it's related to things like, how much the random matrices commute, I think is what it's related to.
Any more? Questions? No, thanks again.
They're an NP, that's right.